This topic will cover what is meant by a continuous random variable. We will look at probability density functions to help find probabilities. For each of these 6 variables, consider whether they will be discrete or continuous. So the result on a 20-sided dice will be discrete. It can only take certain values on that dice. The height of a 22-year-old male, this is continuous. The temperature in a fridge, this is also continuous, assuming that we can measure between degrees. The shoe size is discrete, this is going to take certain values. Now, minutes late to a lesson, this really depends on whether it's being rounded or not. So if it's the amount of time late to a lesson, this would be continuous. However, if we were rounding to the nearest minute, we would say that this was discrete. And finally, the weight of a car in a car park also be continuous. We have previously seen that for a discrete random variable x, we can use a probability function to define the probability. For example, the probability that x equals x would be 2 over 3x squared for x values of 1, 2 or 3, 5 over 54 for the x value of 4 and 0 otherwise. For a continuous random variable, x doesn't have discrete values that it can take, so we have to define the probability function in terms of a range of values of x. So we may have, for example, f of x is 2x over 3 for all x values from 1 to 2 inclusive and 0 otherwise. So here we have a range of values of x rather than specific values. This is called a probability density function. We use this for continuous variables. Probability density function is often abbreviated to PDF. If we have a continuous random variable x, then we can sketch the probability density function f of x as a graph. So using the PDF from the previous example, we can put x values along the horizontal axis, we can put f of x up the vertical axis. Because 2x over 3 is a straight line, we can show this part between 1 and 2 on the x-axis. And we can then use the area underneath the graph to calculate the probability that x will be a certain value. So we're going to calculate each of these probabilities to 3 significant figures. So in the first case, the probability that x is less than or equal to 1.5, we just need to calculate the area under that graph for all x values less than or equal to 1.5. So in this case, we have the area of this trapezium. We could use half of a plus b multiplied by h, the distance between. Alternatively, you could use integration for this. You could integrate the function 2x over 3 between just 1 and 1.5. The reason it's between 1 and 1.5 is because it's 0 before this, so we're only calculating this part here. You may want to pause the slide and calculate each of the other values here. So for the next one, the probability that x is between 1.1 and 1.2 is just the area of this thin trapezium here. Again, we can either integrate between 1.1 and 1.2, or we can use the area of a trapezium. We find the heights of the trapezium by substituting the x values 1.1 and 1.2 into the function 2x over 3. This gives us the heights of each of the parallel sides. Probability that x is greater than 1.8, we basically need to find the area from 1.8 up to 2, because it's then 0 for all values after 2. And then finally, the probability that x is equal to 1.7, this is 0. The reason for this is because we are just finding the area of the line at x equals 1.7. Because lines have got an infinitely thin area, the area will be 0. So for any continuous random variable x, the probability that x is equal to a specific value is always 0, because this is just the area of a straight line. For each of these graphs, consider which of these could represent a probability density function for a continuous distribution. So the first one, the total area under a PDF must always add up to 1. This is because probabilities always add up to 1. So if we were to integrate this function from minus infinity to plus infinity, in other words, all of the x values it could possibly take, this has to equal 1. Now, we don't actually need to calculate this. We can see that if this were to be drawn as a triangle instead of a curve, this triangle would have an area of 1. It's half base times height would give us 1 here. Because the curve is clearly below the triangle here, this graph has got an area less than 1, therefore it doesn't represent a PDF. For the second one, the area under a PDF represents probability. This means that for any x values, probability always has to be greater than 0, because probability is always between 0 and 1. And we can see that for this section here, the area will be negative because the graph dips below the x-axis. So therefore this could not be a PDF because we have negative probability for part of the graph. For the third one, a PDF can be in different sections as long as each of the sections add up to 1. So in this case, if we find the area of the first part, we have 0.125. The area of the triangle, we have 0.875. The total area will be 1. However, because this distribution is described as being a continuous distribution, the continuous function must be continuous across all of its sections. So we would say that this could not be a PDF for a continuous function. However, it could still be a PDF for a non-continuous function. For the final graph, we can see that f of x is always greater than 0. We just need to check the area under the graph. So the rectangle here has an area of 0.9. The triangle has a probability or area of 0.1. The total area is 1. It's also continuous, so we can say that this graph could represent a PDF for a continuous function. In this question, we will define a continuous random variable x with the following probability density function, where k is a constant. We're first going to sketch the graph of f. We're going to use this to find the value of k, and then we're going to find the probability that x is between 1 and 2.5. So for the first part, we're going to start with the horizontal axis, with x going from 0 to 3. This is because when we look at the x values in the function, we can see we have 0 to 3 and then it's 0 for all of the values. We're going to put f of x up the vertical axis. So kx squared is going to be part of a parabola. We don't know what k is yet, but we can still sketch this as follows. We know that it's going to be a positive because otherwise it wouldn't be a probability density function. So this is going from 0 to 2. We then know that for x is 2 to 3, that the probability function is 4k. Because we know it's continuous, we know that it will continue on from the point that we had reached here. We can then label the points up the side using k, 2k, 3k and 4k. We're now going to find the value of k. So we know the area underneath this graph must equal 1. So we're going to integrate from x is negative infinity to positive infinity. Obviously in this case we're only actually going from 0 to 3 because the probability is 0 outside of that range. So integrating this, we know that the function from x is 0 to x is 2 is kx squared, so we'll integrate that. We then know that the function from x is 2 to 3 is 4k, so we'll integrate that. Integrating these and putting in the limits gives us this function here, 8k over 3 plus 12k minus 8k. This simplifies down to 20k over 3, and we know that this has to equal 1 because it's a probability density function. We can then rearrange this to find the value of k. This brings us to k equals 3 over 20, so we can now replace this in the f of x. Now Now for part C, we're going to find the probability that x is between 1 and 2.5 by finding the area under the graph between these two values. So we're going to have to do this in two separate integrals, as there are two parts to the function. First, we're going to go from 1 up to 2, as this is where the functions change. We're going to integrate the kx squared, or 3x squared over 20. We're then going to go from 2 to 2.5. This could be found just by finding the area of a rectangle, or you could integrate the 12 over 20. Both of these will give us the same answer. Finding each of these two integrals, adding them together, gives us a probability of 0.65. So therefore, the probability that x is between 1 and 2.5 will be 0.65. Now complete exercise 4a on page 55.